I'll be talking about how you're supposed to show that a set S spans a superset W. So another way of saying that is showing that a set S generates, we say S generates W, or we can also say that S is a spanning set. S is a spanning set of W. So, for example, if I tell you determine whether the set S, which is equal to 1, 0, 0, 0, 0, 1, 0, 1, 0, spans or generates R3, then usually what you're supposed to do, the first thing you need to do is you need to find a general representation. For the set that you're trying to span, or the set you want to span. So in this case, you can write R3 as all of the vectors that look like A, B, C, such that A, B, C belong to the real numbers. Okay. Now, if I ask you if S generates R3, if S generates R3, then I'm basically asking you, so this is basically asking you to solve the system A, B, C equals C1, 1, 0, 0 plus C2, 0, 1, 0 plus C3, 0, 0, 1, where C1, C2, C3 are scalars. C1, C2, C3 belong to the real numbers. So you're basically trying to see if there is a solution for which you can take you're trying to see if there's a solution C1, C2, C3, for which if you take any arbitrary, so any vector in R3, any element in R3, you want to see if there can be a solution, C1, C2, C3, that you can use to express A, B, C as a linear combination of these three vectors. So it might seem a bit too abstract, because you have, in this case, it's like you have 6 unknowns, right? You don't really know what A, B, C are, and you're trying to find what C1, C2, C3 are. But just imagine A, B, C. So the trick is, imagine A, B, C as real numbers, as a real solution. So as a real solution, or as a vector in R3. So ABC can be 1, 2, 0, or 3, 1, minus 2, or 4, 3, 5. It can be whatever you want. So ABC can be any of these. Right? It can be any possible vector in R3. That's what it means for that's basically the definition of the vector space R3. It's any vector that can be represented as A, B, C. Okay, so now I'm trying to see if the three vectors that I have, so I'm trying to see if the three vectors that I have here three vectors that I have here in S, if they span, or that is, if they can be represented as a linear combination of A, B, C. So in this case, I can actually create a system of linear equations. Create a system of linear equations where I have A is equal to C1 times 1 plus 0 plus 0, and then B is equal to 0 plus C2 1 plus 0, and C is equal to 0 plus 0 plus C3 1. So the only thing I'm doing here is I'm looking for a solution. I'm just trying to see if it's possible to express C1, C2, C3 in terms of A, B, C. Well, in this case, clearly you can, because C1 is A, and C2 is B, and C3 is C. So automatically, if you have a real solution, then automatically, if you have a real solution to this system, to this equation, then automatically you can say that yes, if you have a real solution to the system of equation, well, this sort of big equation, then you can say yes, my set S, which is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1, S spans R3. Okay? Now, let's do another example because maybe this isn't clear yet. So let's try another example. So example 2. Okay. Now, let's say I ask you show that the set S, which is equal to x squared plus 1, x minus 2, x squared minus 2x plus 1 spans P2R. Now, if you don't know yet, P2R is just a vector space. P2R is a vector space. P2R is a vector space, and P2R can be represented as A plus BX plus CX squared, such that A, B, C belong to the real numbers. So this is a similar representation to how I defined R3 over here. R3 is the set of all vectors that look like ABC. Well, ABC, that have ABC, and P2R is the set, so this is like the set of all polynomials that look like A plus BX plus CX squared, where A, B, C can be any polynomial you want. So for example, 1 plus X belongs to P2R. Because you can just make C equal to 0, that's allowed. You can also have 1 minus 2x plus 3x squared, that can belong to P2R. You can have 1 belong to P2R if you make the other two be C0, that's also allowed. So it's any polynomial that can look like A plus BX plus CX squared. Okay, so let's go back to the question. The question is, show that the set S is equal to x squared plus 1, x minus 2, x squared minus 2x plus 1 spans P2R. So in other words, what we're trying to look for a solution to the system A plus BX plus CX squared, So this is just my general representation of any polynomial in P2R. So that's my left-hand side. I'm trying to see if that can be equal to a linear combination of the three vectors or the three elements I have in S. So in other words, if it's equal to C1 times x squared plus 1 plus C2 x minus 2 plus C3 x squared minus 2x plus 1. So basically, I'm trying to see if this has a real solution. So this is a lot like, this is just, if you get scared that you have like letters here on this side and letters on this side, then just pretend that A, B, C are numbers. Just pretend, for example, that they're all 1, 1, 1. Then you're just trying to solve, three different linear equations. So you want to create a system of linear equations. So you want to create a system of linear equations. So remember what I did in previous videos with polynomials and linear combinations. I started with my factor of 1. So I want to see if all the terms with that are linked with a 1 factor can be expressed as a single linear equation. So in this case, A times 1 is the same as A, right? So I can have A is equal to, I have C1 times 1. So A is equal to C1 plus, and here I have C2x. So that's not good. It doesn't have a 1. C2 minus 2 times 1. So I can write plus minus 2 C2 plus, and then I have C3 times 1 plus C3. So that's my first system. So just remember, just pretend that this was like a 5 and you were solving for C1, C2, C3. So always remember that you're solving for C1, C2, C3. Okay? Now, my second equation is going to be for the x's, so it's going to start with b, because b is the term that has x on my left-hand side. And then on my right-hand side, well, C1 doesn't have any x's. C2 does have one. It has C2. So notice that C2 is just alone. It doesn't have a coefficient. And then we have our C3 multiplying minus 2x. So if we ignore the x for a second, then we'll just get minus 2c3. And that's our second equation. And then for the x squared, we'll get c, because on the left-hand side, c is the only coefficient that's linked to an x squared. And then on the right-hand side, we'll have c1 distributing x squared. So I'll have c is equal to c1 plus, then I don't have any x squares here, but I do have one here, so plus c3. And now this is my system of linear equations. I have my constants on one side and my unknowns on the other side. Again, just pretend that these ABCs are numbers. Don't freak out that they're letters and that, so now I'm going to have to put them in a matrix and I'm going to have unknowns on both sides. Just pretend that they're letters. Okay? So now I'm going to put the system in a matrix. So I'll have C1, C2, C3, and then my constants A, B, C. So my first equation had 1c1. So now I'm just reading off the coefficients. Then minus 2c2, then 1c3. Then 0c1, 1c2, minus 2c3. And then 1c1, 0c2, 1c3. Okay, now I'm just solving. I think I might have made a mistake somewhere. Okay, actually no. There's no mistake. There's no mistake. Sorry about that. Okay, so now what I want to do is I just want to row reduce. I want to row reduce, and I want to solve for C1, C2, C3. Okay, that's basically what I'm trying to do. Okay, so what I'm going to do, I'm going to start with this one, and I'm going to say row 3 becomes row 3 minus row 1. So that'll give me 1 minus 2, 1, A, then 0, 1 minus 2, B, and then 0, 2, 0, C minus A. Now, yeah, I just did an operation with C's and A's, so I can't say this is anything yet because I don't know what number it is. I just know that this is a scalar and this is a scalar. So I'm basically just subtracting. I'm just subtracting two scalars. Okay, next, what I think I should do, what it looks like I should do, I'll use this one. Actually, I'll use this one, and I'll say row 1 becomes row 1 plus 2 times row 2, and then row 3, let's say row 3 becomes minus 2, row 2. Okay, now what happens here is this stays the same. I get B, and then I get 0, 0, then I get 4, and then I get C minus A minus 2B, and on top I'll get 1, 0, then 1, so this is minus 3, and this is A plus 2B. Okay, and then what I'm going to do is I'm going to divide my third row by 4, so R3 over 4, to make that just 1, make it nice and simple. So I'll get 0, 0, 1, C minus A minus 2B is equal 4. And then I have 0, 1 minus 2B, and I have 1, 0 minus 3A plus 2B. And what I'm going to do now is I'm going to take row 4 and add, so I'll say R2 is R2 plus 2 R3, and R1 is R1 plus 2 R3. Okay, so what that gives me is C minus A minus 2B over 4, and this is 1, 1, 0. So I'm not going to simplify it because there's no point in simplifying it. So I'll just write it in letters. So I wrote 2 because I just canceled the 2 and the 4. And then 1, 0, 0 plus 2. So again, A plus 2B plus C minus A minus 2B over 2. Okay, now this looks very complicated, right? These are really ugly expressions, but it doesn't matter that they're ugly expressions. So the only thing that matters now, the only thing that I actually wanted to check, is that C1, C2, C3, that C1, C2, C3 have a real solution, right? That C1, C2, C3 have an actual solution. Like you can give them, you can assign them a specific number. And in this case, they do, because in this case, C3 is C minus A minus 2B over 4. And then C2 is B plus C minus A minus 2B over 2. And C1 is A plus 2B plus C minus A minus 2B over 2. And these will all have, so C1, C2, C3 will all have real solutions because no matter what C, A, and B are, so if they're 0, if they're 1, if they're all different numbers, it doesn't matter because in the end, if I do C, if I do a number, so let's say, for example, so this is just an example, if I say, if C is 1 and A is 2 and B is 0, then I'll say C3 is actually 1 minus 2 minus 0, so minus 1 over 4. So C3 will be minus 1 over 4. And then I'll use the same numbers I used here, here, and here. So basically, this just gives you a general solution for C1, C2, C3. And so this means, so this shows us that the elements in the set S can express, so if you take the linear combinations of these elements, they can express any polynomial in P2R. Meaning that the set S spans P2R. Because as we've just shown here, for any A, B, C, we can get a solution for C1, C2, C3 such that you can create a linear combination with these three vectors where you add them up, multiplying them by C1, C2, C3 respectively, and you'll get a polynomial that looks something like this for whatever A, B, C are. So this is basically how you show that a set spans another set or a certain vector space. Usually it'll be a certain vector space.